Thanks very much. Thank you. It's a great pleasure to be back at the LSE and see so many old, familiar faces and new, unfamiliar buildings. A great pleasure to do something which I never did when I was at LSE, which is talk about lakatos. So what I'm going to try and do in the talk, I hope, is to try and identify things which I think in Lakatos's work are relevant or can be elaborated by contemporary philosophical work. And so what I'd like to try and do is start with what I think Lakatos is in general trying to do, and here I've just stolen an analysis from Ian Hacking's famous paper on Lakatos. And Hacking says, well, what's Lakatos trying to do? He's first of all trying to explain the growth of knowledge. And he makes a number of observations which I think are important. First of all, it's just obvious that knowledge grows. So this is just a basic fact, which is the job of the philosopher of science to try to explain. But in explaining how scientific or mathematical knowledge grows, what you need is an analysis that will say what this growth consists of. This is the thing I'm going to try and focus on mostly in this talk. And says Hacking, you have to tell us what this growth is, which makes it science, and how it's different from other kinds of growth. So in Hacking's paper, he says, of course, you could say Talmudic commentary, that's grown a lot, but that's not scientific growth. So what's different about science? And then the third important thing that Hacking says is that the machinery of research programs, hardcores, protected belts, progress and degeneration must, if it's worth, affect a distinction between what Lakatos calls objective knowledge and those which pursue different aims and have different intellectual trajectories. The main reason I've chosen to take this last part of the talk, this last point 3 here, is because it lists very fully all of the things which I'm not going to talk about in this talk. I'm not going to say anything about research programs or hardcores or protected belts or progress and degeneration. What I'm going to do to try and say something about point 2 is to focus on Lakatos's idea of heuristic. And I think this is a reasonable way to try and understand something like the methodology of scientific research programs, or what's important about the methodology of scientific research programs. Because heuristic is, of course, central, very important to proofs and refutations. And it seems it's not just an accident that the word heuristic pops up in the methodology of scientific research programs. So maybe we can learn something about what Lakatos is trying to do with heuristic by thinking about how it does play a role in the philosophy of maths and how it could play a role in the philosophy of science. Okay. So when we look at how heuristic is described in proofs and refutations, the description there, I think, is quite rich and sophisticated. So we're supposed to do something like this. We begin with the primitive conjecture, the Euler conjecture in the text. Then we're offered a proof, an informal thought experiment or argument from which this proof conjecture is then analyzed into subject conjectures and lemmas. What we do is we search for counterexamples, global counterexamples which contradict the thesis of the contradict the conjecture itself, or local counterexamples which contradict one of the sub-conjectures. On the basis of that, we re-examine the proof, we've identified guilty lemmas, and then this is the interesting and important bit, I think, which the notion of heuristic surrounds, is that we improve the conjecture by various kinds of procedures. So, for example, in fact, this was talked about in much more detail and much more interestingly this morning than I'm going to talk about today. We do things like lemma incorporation, so we move from something which is almost tautological, like all polyhedra are Eulerian, and that becomes instead all polyhedra with simply connected faces that are topologically equivalent to a sphere, or something like that. And then we end up with, in the process of constructing these proofs, we change our concepts in the way that Tavi was talking about earlier on. We come up with new concepts. For example, we learn this funny coupled thing over here can count as a polyhedron as well, because the proofs apply equally well to polyhedra with curvilinear sides, they do regular polyhedra. And so the notion of what a polyhedron is extended by this proof analysis. And then we begin the example, then we begin the process again once we've generated these new proofs with these stretched concepts, which make use of these various kinds of processes like lab incorporation. We look for new kinds of science. And this is a detailed, quite a rich story. Maybe it's too detailed and rich, right? Because of course one of the common complaints about proofs and refutations is that it only applies to this one particular case. But if we compare heuristic and proof and refutations with the kinds of things that Lakatos says in the philosophy of science, I think they're disappointingly vague by comparison, particularly if you focus on the notion of positive heuristic. So we end up with things like this. The positive heuristic consists of partially articulated sets of suggestions or hints on how to change, develop the refutable variants of the research program, how to modify, sophisticate the refutable protective belt. Or, I would say even less helpfully, we end up with things like, one may formulate the positive heuristic of a research program as a metaphysical principle. For instance, one may formulate Newton's program like this. The planets are essentially gravitating spinning tops of a roughly spherical shape. Now, by comparison, this is a bit vague. And one of the things which is maybe also kind of disappointing about it is that in proofs and refutations, it looks like this is a general method of discovery that we're being offered. Whereas it's quite clear when you read Lakatos's work in the philosophy of science that heuristic seems to be something which is research program specific. There's not a general account of how it is that a research program is to be developed which can apply to multiple different research programs. So it would be nice if we could try and say something, first of all, which was more precise in trying to give an account of heuristic in the philosophy of science, and maybe in trying to say something which is more precise as well, hopefully something which could apply to more than one particular example. Okay, so here's my suggestion of one way that we could do this and try and connect it to issues in contemporary philosophy of science. One thing we could think about is, well, maybe the Lakatosian idea of heuristic can be developed by trying to think of it as a version of the kind of things that Mark Wilson has discussed in his work. And I think this is an appropriate way to do it because the main task, I think, of heuristic should be to explain how it is that you get something out of the physics which is useful. So the task is to explain how physics gets applied usefully to new situations, to how science or physics grows. And so what I'm going to do is give you one example of this kind of thing, of this kind of general strategy, how to do this from Wilson's work, his example of multi-scalar modeling. And he says some vague things about it too. Here's some of the vague things he says about it. The basic trick is to position a variety of individual modeling tactics called submodels within a coordinated architecture that shifts between these components in a controlled checks and balances manner. Here's the strategy supposed to be probe the intricacies of a complex problem only to the depth required to extract larger scale answers that are normally trustworthy. Simultaneously conduct smaller scale tests to verify that these presumptions of normalcy are actually satisfied. Okay, so maybe that's not that much better than Lakatos so far. So what I'm going to do is I'm going to go through a little bit detail one recent example of this that Wilson has given. If you know Wilson's work, then either prepare to be bored, because I'm not going to add anything new to it, or if you know Wilson's work and you don't feel you understand it, you're hoping I'm going to clarify it, be prepared to be disappointed, I think. But I can give you a sketch of the kind of thing that he's going to do. So, this is the kind of example that, so just to show you how unoriginal I mean, these are drawings actually from Wilson's work. I haven't done any of my own work at all. So you consider situations like this where you're building a casino on a granite block and you're wondering about might actually look at this and think, well, this is actually totally irrelevant to the kind of thing that Lakatos was talking about. This looks like an engineering problem, and it's got nothing to do with physics. If you think that, maybe we can discuss that later on in the question section. But I think the kind of things that he says here about this granite block case also apply to lots of things in physics, or at least that's what Wilson claims. Okay, so what do we do, according to Wilson? Well, first of all, what we do is we start off with a simple model, a primitive conjecture, if you want it. And we say that we're going to model the slab as a kind of simple Hookean solid. We're going to say that it's going to obey the Navier equation. It's going to obey these equations listed down here. And what we're going to do, first of all, with our simple model is we're going to try, as he puts it, probe that model to try and work out areas within the granite block which are going to endure high stress. So this is a highly non-trivial thing to actually do. So we make this calculation and we're able, first of all, to identify parts of the granite rock which might have which might be experience a high degree of shearing, which is illustrated here. Okay, so that's our first step. Then step two, according to Wilson, is that what we try and do is we move to a different scale. So we move from the macroscopic scale to this mesoscopic scale. And we try to model our critical area, the area which is going to have possibly continuous high shearing stress. And then what we have to do is introduce a new model. And our new model is going to think of the structure in a different way. Okay, so we're going to model the part of the granite that we're interested in is a laminate. It's going to have these grainy component parts. And then we're taking information about the stress suffered by this laminate from our higher order model. And then what do we do? Well, what we're going to try and do is we're going to compute how it is that this structure is affected by those stresses. He's going to say one of two interesting things can happen. It's not really affected at all. The orientation of these elements is unaffected in any great way. They're being random. Or what we end up with doing is that the stress causes these parts of the granite block to line up, and that can create a grain in the rock which affects its elastic properties. In that second case, what you need to do then is, that second case shows you that in some way your simple model of the original rock is inadequate. And so what you need to do is take the information you've got from your lower order model and put it back into your macroscopic model. And the way you do that, according to Wilson, is by what he calls homogenizing, averaging out the effects, and then adding these back into your new model as a new set of parameters. And then once you've done that, you begin the process again. This new information will affect the areas within the rock you might think you're going to experience a high shearing stress. That will lead you to look at new parts of the rock and examine those lower scale properties, and you go through this process again. So here is his model, right? You start with your initial model, like language of Lakatos, it's called this your initial conjecture. Use that initial conjecture to locate regions of high predicted stress. Then you move to a different model, a lower scale model, and you say, will the region selected develop across granular alignment and orientation? If no, then it's fine, your original model is okay. If yes, then you need to homogenize that information sequence and feed it back into your higher level model. And you keep doing that until you get something which to the end of the here. Okay, so that's what Wilson says. Why is that interesting? Well, one way you could interpret what Wilson has said is by direct analogy with proofs and refutations. So what you could say is that we begin with a simple model instead of a simple conjecture. What we find is that our lower scale models refute the simple model. They provide information which contradicts our initial assumption about the original model. And so we alter the original model, but we don't do it in an arbitrary way. It's not just a process of conjecture and refutation and guessing and changing. What we're doing is directly incorporating information from the lower level model into the higher level model. We could call it, instead of lemma incorporation, we could call it model incorporation, if you wanted. So we could say that, and when I started writing about this, that's what I wanted to say. But I think it's a very strained or highly stressed way of trying to understand what's going on. And actually probably it's better to think of it the other way around, which is to say that when Lakatos is talking about heuristics in science, he's really talking more about the kinds of things that Wilson calls physics avoidance. So the general pattern of which this is a particular instance is that we're going to start, generally speaking, in science with a very physics, with a very simple model with a very few degrees of freedom, because that's easy to represent mathematically. And we're going to adjust and improve this model by various kinds of strategies. And often those strategies will appeal to various bits of background knowledge that we have. You can see that in the granite case, right? We know this is the appropriate. Something like this is an appropriate, that's not the actual model, but thinking of the structure like this is appropriate because of things that we already know. We don't need our physics to tell us about the structure of granite that is made up from these granular parts. Ooh, got too far. So very often you have this background knowledge, you know about the structure of granite, and you improve your model from getting various other pieces of information in. So in this particular case that we've looked at, we are using information we're getting from models from lower scales, but it can also involve things like boundary conditions, fixed points, knowledge of final states, and a judicious ability to ignore things which are irrelevant. For example, we're not interested in the low stress regions of the granite when we're doing these kinds of modeling. And if you look at the kinds of examples that Lakatos gives when he goes a little bit beyond, he gives an actual example of what heuristic is when he goes beyond the simple and vague sounding statements that I listed at the beginning, they seem to be, I think, quite good examples of this kind of physics avoidance that Wilson was talking about. So here's a passage, or an edited passage that you can find in his work on research programs. He says, you first have worked out his program for a planetary system with a fixed point like sun and one single point like planet. It was in this model that he derived his inverse square law for Kepler's ellipse. Then he worked out the program for more planets, as if they were only heliocentric but no interplanetary forces. Then he worked out the case where the sun and the planets were not mass points but mass balls, and so it goes on for other kind of situations. So this is, I suppose, the fleshing out of what was the metaphysical principle at the beginning. The idea that Newton thought of the planets as, I've actually forgotten what I've said, but anyway, Newton thought of the planets as rotating gravitational balls, whatever it was. But what we can see here is happening is something very much like what Wilson means by physics avoidance. We're starting with a very simple model with a few degrees of freedom, point-like planets. And then we're adding in extra information. And that extra information that we have, it's very misleading to talk about this as refutation, right? Nobody thinks that this is an accurate description of the planet. When it's presented, no one is thinking this is how things really are. Now it's different from, say, the initial conjecture, say, in proof and refutations. We know that this is false, but we're doing it because we think we might be able to usefully apply mathematics to a situation like this. And then what we do when we want to improve the model is that we go through stages of de-idealization. We add in extra features. And often the extra features we add in are bits of information that we have in our background knowledge. We know that since we're on the planet, we know it's not a point. When we know various other kinds of things as well, which are adding here as well. I mean, we could even go beyond the kind of things that Lakatos talks about and think about, say, planets like the Earth and how the fact that their surface is mostly covered with water might affect various kinds of some of the physics of those planets. So Lakatos described, whenever it actually gets down to describing something which is heuristic, is very like the kind of thing that Wilson is talking about with physics avoidance. We start with a simple model which is false, obviously false, we know it's false. But because that allows us to apply our physics in a simple way, and then we gradually de-idealize. And so I think it's very misleading to call this a kind of metaphysical principle. There's nothing really which is in the way that a metaphysician might be interested in things, a metaphysical principle here. What there are just particular descriptions of how the world is, local facts that we know which are feeding into our model. And so I would actually say, we're now at the stage of the talk where I've run out of arguments. And so I'm going to just stick some quotes on the board and hope to convince you that way that what I'm saying is correct. So I think what we might draw from this, in fact, is a few kinds of lessons from the idea of heuristic, which I think are actually already in Lakatos's text as well anyway. So the first kind of lesson you might have is that, well, when you think about it, although it's called proofs and refutations, and although refutations seem to be central to the methodology of scientific research programs, really they're not that important, or really they're certainly not essential to what's going on in science. And we see this a bit in the last stages of the dialogue. We have Pi says, full of counterexamples once you recognize that any increase of content, any deeper proof follows or generates heuristic refutations of the previous poorer theorems to which alpha responds. Theta expanded counterexample to cover heuristic counterexamples, you now expanded to cover heuristic examples, counterexamples that never actually exist. And so, what's meant here, what's really being illustrated here is that it's this idea that there's an increase in content some way, which is the important idea. You could say it's a refutation because it's saying things, more things, or different things. To the earlier theory or earlier conjecture. But it's not necessary to understand how you get that increased content to appeal to the notion of refutation. So here's another quote which I think illustrates the same thought for physics. He says, the real difficulties for the theoretical scientist arise rather from the mathematical difficulties of the program than from anomalies. So the fundamental issue is not really, I have something which refutes my theory. It's how do I get my theory to say anything at all about the situations which I'm interested in. And so this is what I think a good account of heuristic would be. It would be a story about, given some mathematical theory, how it is we get it to talk to the problems that we're interested in, how we get it to apply in the first place. And that is what Wilson has illustrated for at least one kind of case. Okay, so here's more quotes. One other thing I think lesson we could draw from this, I'd be interested to know what you think, is that although reputations may be not very important, what Lakatos calls concept stretching is important. Here's another one quote. The recognition that the history of science is the history of research programs rather than theories may therefore be seen as a partial vindication of the view that the history of science is the history of conceptual frameworks or of scientific languages. One of the things that we need to do in order to make sense of growth is that we need to also make sense of concept stretching. You're not going to get growth, or in at least a lot of cases, you're not going to get growth. Maybe this is what you talked about beautifully earlier on, unless you have some innovation in the concepts. And so a good account of heuristic should also explain how that concept stretching takes place. Lakatos does that in proofs and refutations. It's less clear, to me at least, what the connection is between what he calls heuristic and concept stretching in the methodology of scientific research programs. But if we look into Wilson's work, unfortunately, because I've only got 5 minutes left, I wouldn't necessarily have to describe this, then he suggests that the kind of situations that he's interested in, trying to get bits of mathematics to apply to real-world situations, often involve all kinds of concept stretching. So notions like force or temperature or hardness take on new or more specific meanings as they're applied in new context. Okay, now this is a quote overload here. Okay, so what we want is the kind of heuristic, and what heuristic does, hopefully, is make sense of us for us how it is that science or mathematics grows rationally. How it is that it involves notions like incorporation, whatever it might be, or the kinds of structures that Wilson describes. So you might think, well, what's the importance of this? Well, another kind of analogy that you can see between Lakatos's work and Wilson's work is that Lakatos rails against what he calls Euclideanism. Wilson rails against what he calls theory T thinking, the idea that a theory is you just come up with a theory, you plug in a set of initial conditions, and then you deduce everything that you're interested in. And this is just because I wanted to quote someone else, I guess. I think it's also similar to what Ritchie talks about when she talks about the pristine interpretation of, say, something like quantum mechanics. That you want one unique interpretation of the theory which is going to answer all the questions, be relevant to every application. So what's wrong with that? Why should we care about that? Well, I think what these quotes illustrate is that one reason that we should care about that, I really wanted to say this word.
It's got to be wrapped up.
Right, yeah, I really wanted to say that word. I don't have time. Well, one reason we can do it is just to be more accurate about how science works. It's obviously one reason to do it. If you think in terms of what Lakatos calls Euclideanism or theory T thinking, then you just get certain aspects of the structure of science wrong. And maybe also you get certain aspects of the structure of how language works wrong. That's one thing that Wilson really wants to emphasize. But here's one other speculative lesson that you might draw from it, is that philosophy of science is important in broader philosophy because lots of other philosophers, they look at science, jealously they look at science, and they try to say that what they're doing, the way that they think about things, they're trying to model it on science. So here is this is probably the most quoted bits of metaphysical methodology in the literature from Ted Siler. And he says this: just like scientists, metaphysicians go on to construct general theories based on observations. Even though the observations don't logically settle which theory is correct, kind of version of the undetermination of theory by data, supposedly, in doing so, metaphysicians use standards for choosing theories that are like the standards used by science: simplicity, comprehensiveness, elegance, and so on. Now, this is a terrible image of science. This is theory T thinking. It's Euclideanism. And there's lots of very good accounts in the literature already of how the notion of simplicity, for example, works in real scientific cases. Alex Sober, John Norton, really important work. But maybe the general idea that the metaphysician has is a good idea. If metaphysics is worth doing, then maybe metaphysics ought to try to model itself on science. So maybe something else, another lesson you could get out of this work, is that if there's going to be something which is something like a naturalized metaphysics, then what metaphysicians ought to be identifying is something like a metaphysical heuristic. What they need to do is search for ways in which concepts like cause, possibility, in ordinary, less ordinary talk actually work, how they feature in real concrete cases of application, and how they change through those concrete applications. So that's my story. That's my story about what's important and interesting about Lakatos, the idea of heuristic. We can see that idea of heuristic is developed, even though he doesn't use the same term, in interesting ways by Wilson. And maybe if we think there's something right about the general naturalist project that people have in metaphysics, what metaphysicians should be trying to